In this presentation, we're going to look at partial fraction expansion. But a very important thing to talk about before we talk about partial fraction expansion is the business of polynomials. So these are essentially forms of equation, and for what we are going to concern ourselves with there are four different types. There's actually more than four different types. There's actually loads, but there's just as far as pen and paper exercises are concerned, I mean, really, it'll usually be these four. So we have constants, linear polynomials. Constants are just constants. Linear polynomials are linear equations. Quadratic polynomials are quadratic equations, and cubic equations. Okay, and each of them has a degree. So a polynomial of degree 0 is constant, and a constant is also known as a polynomial of degree 0. A linear polynomial is a polynomial of degree 1. Likewise, a quadratic is a polynomial of degree 2, and a cubic is a polynomial of degree 3. So let's just look here at a couple of the examples. This is the form of it. And we have a, and I'll just give you a quick example here. We actually could write that as a times x to the power of 0. Hence, this 0, x to the power of 0 is 1, so a times 1 is just a. X to the power of 0, that 0 there is the highest power of x in this expression. So that's why we call it a polynomial of degree 0. It's the power of the highest. It's the highest power of x in that expression. Is the polynomial is the degree of that polynomial. A constant is simply a number like 2 or pi or e or something like that. So that's straightforward enough. A linear is which is a polynomial of degree 1, ax plus b, and again we have ax to the power of 1 plus b, hence the polynomial of degree 1. It's the highest power of x there is b. You could actually sort of say we have b times x to the power of 0 as well, if you wanted to look at it that way. Okay, so that is the highest non-zero power of it. So you could like have 0x squared plus, so it actually has to have a non-zero evaluation to it as well. Ax plus b, so for example x plus 1, 2x minus 1, those sort of things. Those are a couple of examples there. A quadratic we all know and love. The highest power there is 2. So for example x squared minus 1, and you could have something like 3x squared plus 6x plus 7, all that sort of thing. And finally, a polynomial of degree 3. The highest power there is 3, ax cubed. And let's go write something long here. So just let's do something mad. 3x cubed plus 17x squared plus 6x plus 3. That's a d there, by the way, sorry. So a, b, c, and d are just like coefficients. And that's an example of a polynomial of degree 3. One way, something you could sort of do here is actually you could write them as, for example, a polynomial of degree 0 could be written as p0, p of 1 for linear, and so on, p of 2. So you just actually write polynomial of degree 2, and so on, polynomial of degree 3. Sometimes you might see that in books. I'm actually going to use that now in a second, because we have to get back to the business of partial fraction expansion. So here we have 5x plus 17, and we are going to have the denominator here of this expression, that's the numerator. The denominator is x squared minus 1 times x plus 2. Well, this is a polynomial of degree 2, and that's a polynomial of degree 1. Okay, so far so good. What we're going to do is expand this as the sum of two expressions. Okay, and necessarily x squared minus 1 goes over here, and the second expression will have the denominator as x squared plus 2. But what do we put above? We're used to putting a's and b's there. But what we should put in, this is a polynomial of degree 2, and this is the way the rule actually works. This is a polynomial of degree 1. What we should put in is a polynomial of 1 less of a degree. So what we should put in is a polynomial of degree 1. Here we should put in a polynomial of degree 0. So essentially, if this is a polynomial of degree n goes below, a polynomial of degree n minus 1 goes above. Okay, So here we have a polynomial of degree 2. What we should put in here is something like ax plus b, where we have to figure out what a and b are. Over here we have a polynomial of degree 0 to put in, so the next coefficient in our list, so ax plus b, the a and b are undetermined coefficients. The next one we would put in just c. So, and then you can solve it from there by cross multiplication and so forth. C. This is just an example I made up on the spot actually. So I'm just going to change the numerator over here just to make it a bit more sensible. Not that it really matters. Essentially, it's not the part of this exercise. Okay, so let's just keep an eye on this rule as we go along. Okay, here we have three expressions, or three components. So, x cubed plus 2 plus something over x squared plus 1 plus something over x plus 2. I'm just going to tilt the thing to there we go, just make a little bit more room. This is a polynomial of degree 3. So what should go in here is a polynomial of degree 2. This is a polynomial of degree 2, so what should go in here is a polynomial of degree 1. And likewise, this is a polynomial of degree 1, so we'll put in a polynomial of degree 0 there. I'll just come to that now shortly. Polynomial of degree 2, so ax squared, so the highest power is 2, plus bx plus c. Okay? Polynomial of degree 1, so that's a something times x plus something. So dx plus e, that's a d there by the way, sorry, doesn't look great. And then finally polynomial of degree 0, f. Okay. Now this is a bit like long-winded for pen and paper exercises. It's just actually to emphasize the point about the polynomials above and below, the degree of polynomials above and below in partial fraction expansion. So, but that is the main part of it there. Now there's a couple of things actually you should also make note of. First off, that's the key part of this presentation. Now, the second thing is that sometimes you get polynomials that are powers. Okay, so what do you do here? Well, let's put this a over x minus 1, polynomial of degree 0. But what do you do here? So what you have is a repeated power. Okay. So x plus 1 squared, yeah, not just that easy. So what you have to do here is, first off, for ascending powers of x plus 1 until you get the whole way up to the highest power. So we would have x plus 1 plus something over x plus 1 squared, okay? Over b and then c. You can disregard the rule about that we're doing something different here, so it's not that it's a polynomial of degree 2. This is ascending powers of x plus 1, okay? And it's how you would work with something like this. Okay, so here's another example. We're doing something very similar, but here we have x plus 1 cubed. So what we need here, let's just follow this rule, see if we got it. A over x minus 1, so far so good. But we have x plus 1 here in the middle. So x plus 1, okay, b. Now, the thing we do is go up to the next one, next power of x plus 1, that's x plus 1 squared. So we have plus c over x plus 1 squared, and then plus d over x plus 1 cubed. Okay, so that's how you treat these ones. Now, something I just emphasize here. This part here, the inner part here, x is x plus 1, and that is a polynomial of degree 1. Okay, so all of these should be polynomials of degree 0. Okay, even though you have a cube here. Okay, these should be all polynomials of degrees 0. This is just repeated roots, repeated factors. Okay, that's how you get yourself set up with partial fraction expansion. Now, there's a different rule for solving for coefficients like a, b, c, and so on. There's a couple of rules you can use. A nice handy one is the cover-up rule, but we'll deal with that another time. We got all the main things. We have our partial fraction problems set up now.